In this video, I'm going to talk about stability for linear time variance system. In the previous two videos, I talked about the stability for linear time invariant system. So I talk about both the input and the output stability as well as the internal stability. Okay, so here's a brief recap of the stability of linear time invariant system that I talked about in the previous two videos. So for a given linear time invariant system, which is x dot t a xt plus b ut and y t cxt plus dut, this is the standard format for the linear time invariant system using the state space representation. So we talk about the input output. So the first one, BIBO, which is a type of input and output stability. And both marginal stability and asymptotic stability, they are related to the internal stability. So for both. Okay. So for the linear time invariant system, the BIBO stable means the bounded input will yield a bounded output, which is called a BIBO stable. So we talk about the conditions. Of course, we can verify a system BIBO stable based on the definition. In the general way, we can a more systematic way we can verify if the linear time invariant system is BIBO stable is to check the poles of the transfer function. So basically, first compute the transfer function by using this form, which is C times Si minus A inverse times B plus D. What we need to do is to check if the poles of each entry of the transfer function. The transfer function could be a matrix. Okay, it can have numerous entries. Okay, so we have to check every entry. The poles of every entry in the transfer function have negative real parts. So this one we check the poles which typically each entry is given by some numerator divided by denominator. So both of numerator and denominator are polynomials of the S. So once we set the denominator to be 0, we can find this what do we call the poles. Okay, we need to verify the poles for each of this will have negative real parts. Then this is BIBO stable. If any of the entry have poles that with either 0 or positive real parts, then the system is not a BIBO stable. Okay. For the marginal stable, marginally stable, and asymptotic stable, so we can also use check the eigenvalue. We can check the eigenvalues of matrix A to verify a system is marginally stable or asymptotic stable. Okay, so marginally stable basically means if I have a 0 control input, and if I give some initial conditions x0, if my state, all the future state will be bounded, will be called marginally stable. Okay. If the future state are bounded for all time, and also the final state as t goes to infinity will approach 0, which will be the asymptotically stable. Okay, so that's the difference. That's the definition of the marginal stable and asymptotic stable. The way we check if the system linear time invariant system is marginally stable or asymptotically stable is to evaluate the eigenvalues of the matrix A. Okay, this matrix A. If the eigenvalues of A have 0 or negative real parts, and those eigenvalues with 0 real parts have the same geometric and algebraic multiplicity, then the system is marginally stable. So in terms of these two definitions, what is the algebraic multiplicity and the geometric multiplicity? So you can check my previous video. Okay. On the internal stability. Okay. So for the asymptotic stability, we need to verify if the eigenvalues of A have negative real parts. Okay. All right. So that's a basic recap of the stability for linear time invariant system. Now let's take a look at the case when we have a linear time variant system. Okay. So when we have linear time invariant system, now the A, B, C, D in the linear time invariant system become time invariant. Okay, we generally have AT, BT, CT, and DT to replace original constant matrix A, B, C, and D. Okay, Alright, as I mentioned before in the solution to the linear time variance system, so actually if we have the transition matrix, which is given by phi t tau over here, so I can find a solution to the system. Okay, now I can verify it's a BIBO or marginally stable or asymptotically stable. Okay, so solution for xt is given by phi t0 x0 and integration of 0 to t phi t tau b tau u tau d tau. So that's solution to xt. And the yt, we just have to replace x by its solution and we find the y sub t. So here phi t tau is called a transition matrix, which is calculated by looking at just ATXT. So this is a transition matrix for this guy. Okay, A dot X dot T equal to ATXT. We find a transition matrix. Okay, so once we have this, okay, so we can sort of also define the BIBO stable, which is kind of input-output stability, and also the marginally stable and asymptotically stable. Okay, so the marginally stable again is defined as this. So if any bounded input will provide a bounded output y sub t for any positive t, future t, then this will be okay, this one has to be u sub t. Any bounded u sub t will produce a bounded y sub t, which will be then the system called BIBO stable. Okay, so here's the definition, of course. So here's a condition we can verify. Of course, if you can find a solution, you can directly calculate it if I give the bounded input u sub t to see if the output y sub t is bounded or not. If yes, we can say it's BIBO stable for any bounded one. Of course, you have to be for any bounded one. And now have bounded y sub t. Okay, if that's the case, yeah, we can say it's BIBO stable. Okay, another one we can verify if the system is BIBO stable is to check the following two conditions. The first one is integration of 0 to t, the norm of ct phi t tau b tau norm of this guy. Integrate that over d tau to see if that's bounded. This is less than some positive value, which means it's bounded. So it means this guy has to be bounded. Bounded. And also have to verify if the norm of d sub t is bounded. Okay, we just have verified this guy and this guy to make sure they are bounded. For all t, that will be okay. As a matter of fact, although this sounds pretty straightforward, but the computation of this whole process can be a little bit challenging. As a matter of fact, we can simplify this a little bit. We can write this one as okay, let's go back. This is for the BIBO stable. Okay, now let's take a look at the marginal stability. Okay, now we move to the marginal stability and asymptotic stability. So it's called internal. So this is before this. I want to emphasize. So about this. Okay, this is input output stability. Okay, now we are going to talk about internal stability. So internal stability, as we mentioned for the linear time variance system, the input is assumed to be 0. This is the same case for the linear time variance system. So here we assume my u sub t is 0. I don't have an input. I want to see how the output will change, will behave if I give some initial condition. Okay. So because this ut is assumed to 0, so if I substitute this ut by 0, so these two terms will be cancelled out. We actually have x dot t is atxt, yt is ctxt. So I denote this as double star. Okay, this is the system we talk about internal stability. Okay, so the marginal stable is defined as if the system is bounded stable, if any bounded initial condition will excite a bounded y sub t for any positive t, then the system is called marginally stable. Similarly, asymptotic state defined as this: if any bounded initial condition excites a bounded output for any positive t, and also my y sub t will go to 0 as t goes to infinity, this is called asymptotic stability. The linear time variance system star is asymptotic stable. So this is the same as the linear time invariant system. Okay, the definition is the same. However, because we have a and t and b sub t, so the condition typically different from the linear time invariant system. Okay, so here we also make the assumption that my C sub t over here is bounded for all positive t. The reason that I assume that because if Ct is not bounded, then this is typically not a marginally stable and asymptotic stable. The reason is, if this guy is not bounded, as you can see, I should be able to find some xt, right? Such as this guy is not bounded. This guy will go to infinity. That also means I can select some initial condition which can be bounded, and at time this one will give me an infinite number of y sub t, which means this is not a marginal stable, it's not a asymptotic stable, because the marginal stable means this definition says it has to be a bounded y sub t and a bounded y sub t over here. So if this guy is unbounded, yeah, my star will be definitely unbounded. The state will be unbounded, which means the system is not marginally stable or asymptotically stable. So when we assume this Ct is bounded, so because a bounded xt will imply a bounded of t, because if Ct is bounded, yeah, you time xt is bounded, right? So y sub t is bounded. If ct is bounded, so a bounded xt, which means a bounded y sub t. So we only need to look at this to make sure that as long as my xt is bounded, then my y sub t is definitely bounded because Ct is bounded. So which means, hey, we don't have to look at this system. We just have to look at this much simpler system, which is x star t is atxt. I denote this as star star star. So in other words, the marginal stability for this guy, as well as the marginal stability and the marginal stability for this guy, they are equivalent. Also, the symptotic stability for this guy and the symptotic of this guy, they are equivalent. Okay, so we should not just look at this to see under what condition this star 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 is marginally stable, and under what conditions the star star is symptotic stable. So that's what we're going to talk about in the next. Okay, all right. So here, of course, according to the definition of the marginal stable and symptotic stable, it says a bounded x0 initial condition. So here, let's assume my x0 is bounded. So if this means xt is bounded for all t, of course this t is greater than or equal to 0, then I call the system is marginally stable. Okay, so this is the definition, and the condition is this star 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 is marginally stable if and only if this phi t0 is less than or equal to m for all t, which this phi is my transition matrix, which means, hey, if my transition matrix is always bounded, the norm of transition is always bounded for any time t, this is marginally stable. You can sort of see this is equivalent to say, hey, my original system over here is marginally stable if my transition matrix has a bounded norm for all t. Okay. So similarly for the asymptotic stability, the definition is straightforward. It's just the x for a bounded t. I didn't include the definition, so it just says x0 bounded implies xt bounded and xt norm go to 0 as t go to infinity, then the system is asymptotic stable. Okay. Alright, so that's the definition. So the condition is the star 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 is asymptotic stable if and only if, first of all, the norm of the transition matrix should be bounded for all t. This is the same condition as I mentioned for the marginal stability. And also I have the second condition is the norm of the transition matrix for phi t0 will go to 0 as t goes to infinity. Then the system is asymptotic stable. Okay? So it turns out, as we can see over here, it turns out of course, for the BIBO stability, we have to compute the transition matrix and then compute all this C times CT, B tau, and to verify that's bounded, okay, and also DT should be bounded. So for marginal stability and symptotic stability, we sort of have to have this. We need to calculate this transient matrix. And the transient matrix over here to verify it is a marginally stable or asymptotic. So the computation of transient matrix is pretty important to verify the system is BIBO stable, is marginally stable, is asymptotic for linear time variance system. Okay, so as a matter of fact, the norm of the transient matrix is bounded if each entry of this transient matrix is bounded for all the t. That's pretty straightforward. The other one is if this guy is not bounded, if one entry of this phi is not bounded for some t. This is sort of the equivalent. Okay. Alright, so now let's take a look at a few examples to see if the system, to use the condition we mentioned before to verify a system is stable, okay, for linear time variance system. So let's start with a simple case, a simple example. If I give a linear time invariant system which is x dot t is ATXT, so of course here I don't have an input u, okay. Suppose that my phi t0, I already give you the transient matrix, okay, you don't have to compute it, so it's already computed, it's already given. The transient matrix is given by e sub negative tau, e2 tau, 2t, 0, and e sub t, okay. Is the system linear time variance system marginally stable? Okay, so the condition says my norm of the transient matrix should be bounded for all time t, okay. So, and also this one says, okay, this guy norm is bounded if each entry of this guy is bounded. So if any entry is not bounded, so this norm won't be bounded. Okay, if you look at this one, so I need to verify. You basically can say I want to verify if each of this is bounded. If yes, it's bounded. If any of the one of this is not bounded, then it's not bounded. Okay, so it's not marginally stable. So if you look at this one, this is bounded because this one negative to t. So for any positive t, this is bounded. This guy is also bounded. This also, of course, is bounded. This guy is not bounded because the t go to infinity, this go to infinity. Because this entry will go to infinity as t go to infinity. So I can say one entry of this phi is not bounded. So my phi norm is not bounded, which means it's not marginally stable. So I can say it's not marginally stable. Of course, because it's not marginally stable, so it's not asymptotically stable. Okay, because the first condition of my asymptotic stability is the same as marginal stability. So if margin is not marginal, so it definitely is not asymptotically stable. Okay. All right. So now let's take a look at the case that if we have, so originally for this one I have 0 input, so it makes me only this. We only verify the marginal stable and asymptotic stable. Now we can take a little special case. Say x dot t, a general case. X dot t is ATXT plus BUT, and YT is CXT plus DUT. Okay. So this, let's say this is my system is given by star, and my transient matrix phi is still be given by this. Okay, it's the same. So I don't give you a B and a C and a D yet. So my question is the linear time variance system given by star always not BIBO stable for any BT, CT, and DT? Okay, right? It's not marginally stable. It's not asymptotic stable. But can it be BIBO stable? The answer is yes. Is no, because we can't find the BT, CT, DT to make the system BIBO stable, because this is different from the previous definition right over here. So even if this guy is not bounded, okay, but if I make this to be 0 and this to be 0 and this to be 0, yeah, I still can't have this all bounded. That's the reason. Even the system is not marginally stable, not asymptotic stable, but it can be BIBO stable, because I can make this B's and C's and T's to be 0. If we let this to be true, it is BIBO stable. Okay, so which means even if the system is not marginally stable, we cannot say this system is not BIBO stable. There are not a direct relation between this input-output stability and internal stability. Okay. Now let's take a look at the second example. If I give the linear time variance system, which is x dot t is -1 e to the 2t 0 -1 time xt. Okay, so this is linear time variance system because I have here, this is not a constant. So this constant, this constant, but this is not a constant. So it's still linear time variance system. So I want to verify if the system is marginally stable and is it asymptotically stable. Okay, so if you look at this form, actually you can find the eigenvalue for this matrix a sub t. Okay, although it's time varying, but you can find the eigenvalues. They are actually static; they don't change. the eigenvalues of a sub t, because this is upper diagonal matrix, so the eigenvalues just be -1 and -1. Okay, so if we have this one, can we say the system is marginal stable and asymptotic stable? Okay, the answer is no. Even if you remember for the linear time invariant system, okay, we can check the eigens of A. So as long as this guy has negative real parts, so we know this is marginal stable and also asymptotic stable, basically. You can say that. So this is true. However, for the linear time invariant system, even we still have the eigenvalues of A, and they are all negative real parts, we say this. But we cannot say this is marginally stable. We cannot say this is asymptotic stable. Okay, because linear time invariant. So we have to check the transient matrix. Okay, so the goal is we need to compute the transient matrix to verify it is a marginally stable or asymptotic stable. Okay, so how do I compute the transient matrix? So I talk about a couple approaches for linear time invariant system. Okay, the first approach is we use the Peano-Baker series. Okay, this is a pretty general case you can apply. But the problem is typically it's very hard to find the pattern in certain cases. So it may not be straightforward to find the transition matrix, especially in the explicit form. Okay, so you probably have a very infinite norm. You cannot find any pattern in terms of transient matrix. Okay, at least this is one approach for some cases. Okay, the second approach I mentioned is when we have a diagonal a sub t. So you basically, if a sub t is equal to a11t, so on and so forth, a_n_t. So this is diagonal matrix. They are all 0 over here. So my phi t and 0 will be given by e to the integration 0 to t a11 tau d tau, and so on and so forth. You do e to the integration 0 to t a_n_n tau d tau. So it is a still diagonal matrix, and this is all 0. Now that's what we talk about for the second approach. Other than that, we don't have any good approach for other ones. Here I want to talk about the last approach that you may be able to try, and in some cases, this approach is called we find a solution-based approach. What this means is, I don't know how to do this, but we know what the transient matrix means is xt equal to phi t0 x0. We know the transient matrix must satisfy this property, or you can change it to tau x tau. Okay, that's money. So in general, in a typical case, we just do this. Okay, right? So if I give an initial condition, now I could find my output x of t, and I can write this in this form. Now, I can go back and figure out what is my phi t of 0. That's kind of the principle for the last approach. Okay. All right. So given this one, let's take a look at it. If I give some initial condition, let's find out the actual x of t and see if we can write this xt into this form. Then we can find the corresponding transient matrix. Okay. So that means the whole point we want to find a solution. Okay. So let's say a solution is given by x1t, x2t. Okay. To be the solution, of course, my initial condition is x0. Okay. Which is just x1 0 and x2 0. This is my initial condition. I want to find out what is my solution of xt. Okay. All right. Because my solution must satisfy this equation right over here. So which means x dot t is equal to x1t, x2t, which is equal to, now I just want to, on the right hand side is this guy time x1 xt, right? So this part is nothing but I computed out this form, this term, this product. So I computed out this product is given by this. Okay. All right, which is just product of these two, right? So once we have that one, we actually have two equations. The first one equation is this, which is x. Let's take a look at the second equation. The second equation is x2 dot t is equal to negative x2. This is the second one because it's quite easy to find. So let's start with this guy. Of course, my x2 0 is an initial condition, right? So we can find a solution. I don't want to talk about too much detail about the differential. It's quite straightforward. Okay. The solution is just given by x2t is x20 times e to the minus t. So I give you some steps over here, but actually it's very straightforward. So I can find a solution x2t quite straightforward, which is just x20 times e to the minus t. Alright, so the first equation is given by this. Is x1 dot t is equal to here negative x1t plus e2t x2t. Okay, e2t x2t. Okay, e2t, this is x2t. Because x2t is already given by this, so replace x2t by this right over here. Okay, so this is my second equation. I do some chain simplification, so e to the 2t to the e to the minus t is e to the t. So I have this x1t is negative x1t, x1 dot t is equal to negative x1t plus et x2t. Okay. Alright, so how do we find a solution to this guy? Okay. As a matter of fact, we can consider it as linear time invariant system because I can say I only have one state. Okay, this is a linear time invariant system because I can consider x1t in my state. This is negative 1 as my A. Okay. I can say, hey, my B is x20 and ut, my input is e to the t is my input use of t. I can write this as a linear time invariant system. We know the solution for the linear time invariant system x1t is e to the minus a times t, right? Time x10, x0 plus integration of 0 to t e minus a t minus tau time b u tau, right? B is x20 and tau is ut, right? But I change it to u tau, so it's e to the tau, d tau. Okay. Once I do that, so I don't want to go to the detail about the computation steps. You can do all the computation by yourself. And it turns out this guy becomes this. The final solution x1t is given by e to the 9 negative t x10 plus 1/2 x20 times e to the negative t times e2t. Of course, this one can be simplified as this guy will be cancelled out. It's just e to the t. Okay, so which is given by this. So to summarize, given by this. Or summarized by don't talk about that because I still have one over here. Don't want to drop it out. So what happens here is this guy can be written as this. x1t is e to the minus. The first term doesn't change. Keep it over here. The second term is plus 1/2. So this is e to the minus. We time this one, multiply this inside. It becomes e to the t minus e to the minus t. Okay, it's 1/2 of et minus e minus t times x20. x20 is what I calculate over here, which is x20 times e minus t, so which is x20 and e minus t. Okay, I can multiply 0 times x1t because it doesn't change it. So if you write this one, we can say, hey, the solution is x1t, x2t. It happens that we can write this in this form as we want, because we want to write this one in this form. We want to write this form, xt equal to something times x0, right? So xt, if you do it over here, xt, which is x1t, x2t, this is xt, is equal to, if you do this one, so this is x10, x10, x20, x20. So you just do x10, x20. So you do this like a coefficient. So the coefficients for x10 here is e to the minus t. For the second one is 1/2 e minus et minus e minus t, and this is 0. This is e minus. You do the multiplication. This will become exactly equivalent to these two equations over here. So I indeed can write this solution xt as something time, of course this guy is just equal to x0. So which means I can write this solution as xt equal to e minus t 1/2 et minus e minus t. This is 0 e minus t time x0. So if we compare this one with what I mentioned over here, yes, we indeed can write this xt as this form. So this one will be my phi t0. Okay, all right. So I just need to verify if every entry of this guy is bounded or not. So if you verify over here, so this guy is bounded. Yes, this guy is bounded. And this guy is bounded, but this guy is not bounded because the e to the t will go to infinity. Although this guy will be 0, will be bounded, but this guy is not bounded, so this is not bounded. Because it's not bounded, according to what I said over here, what do we mention over here? if one entry of this phi t0 is not bounded for some t zones, phi is not bounded. If it is not bounded, which means it's not a marginally stable, it's not asymptotically stable. So the conclusion is the system is not a bounded marginally stable, it's not an asymptotically stable. Okay. So lastly, I want to talk a little bit about a summary about the relationship among the BIBU stability, marginal stability, and asymptotic stability. Okay, so we'll talk about these two cases for linear time invariance and linear time variance system. For linear time invariance system, linear time doesn't matter for each one. For both linear time invariance and linear time asymptotic stability means marginal stability, because the definition says the marginal stability only means a bounded initial condition excites a bounded state, while asymptotic stability imposes additional condition. Says this a bounded initial condition excites a bounded state, and also the state will go to 0 as equal to infinity. So because this have an extra condition, so the asymptotic stability is more stringent than the marginal stability, which means that asymptotic definitely means the system is marginally stable. And for the linear time invariant system, we also have some relationship, which is the asymptotic stability means the BIBO stability, okay, but not vice versa. The reason because the asymptotic stability, the necessary sufficient is the eigenvalues of A have negative real part. Okay, so for the BIBO stability, we know the condition is, the necessary and sufficient condition is CSI minus A inverse B plus D, right? That's my condition, right? This one has to have, this one must have the poles. One of the poles of this guy have negative real parts. The problem is the poles, we also show the poles of this guy must come from the eigens of A. It may not be exactly the same. It may not cover all eigenvalues, but it comes from the eigenvalues of A. If the eigenvalues of A have negative, all eigenvalues have negative, of course, if this poles coming from the eigenvalues, so it must have negative real part. That's why the asymptotic stability means also implies the BIBO stability. However, the marginal stability and the BI stability and my BI stability, they don't have a direct relationship. Okay, because this one we can allow the eigenvalues of A to be 0 real parts or negative real parts. Of course, for marginal stability, those with 0 real parts should have the same algebraic multiplicity and geometric multiplicity, of course, but it allows 0 real parts. But here it does not allow that 0 real parts in general. That's why there's no direct link between the BIBO stability and the marginal stability, even for the linear time invariant system. Okay. So for the linear time, you can also say for linear time invariant system, I do not know the relationship between asymptotic stability and the BIBO stability. I do not really know the relationship between marginal stability and the BIBO stability. As you could see over here in this example that I mentioned over here. So this one is not a BIBO stable, not a marginal, but it can still be BIBO stable. Okay. So that's all about stability for the linear time system, including the linear time inverse and the linear time invariant system.